Hello everyone, and thank you for signing up for this webinar on maximizing the bankability of geothermal projects. Before we start, I would like to introduce you to our speakers today. The first speaker is Ms. Madalena Fell. Lena is a technical consultant and project manager for risk management and technical due diligence projects. Before her current role, she was the project manager leading our Water Services Department's largest project on behalf of the Gates Foundation, developing a technical standard for new and high-tech sanitation technologies based on a risk-based approach. The next speaker on the panel is Dr. Rolf Zollner. Rolf has had 11 years of experience in feasibility studies, PPE, and technical due diligence in various industrial sectors. He's an expert consultant on plant machinery safety and reliability, as well as risk assessment and management. Our final speaker today is Alexander Gottwald. Alex has been conducting on-site inspections and evaluations of industrial plants worldwide for about 8 years. His activities include technical due diligence and risk assessments, including technical condition assessments and cost value evaluations. With their combined expertise, they'll be showing you how to maximize the bankability of your projects through feasibility studies and technical due diligence today. Lena, Rolf, and Alex are part of our global pool of experts in TÜV-SÜD, able to harness 150 years' worth of organizational experience across 1,000 locations worldwide. For those who are not familiar with our company, we are an independent and impartial one-stop technical solutions provider that carries out testing, inspections, auditing, certifications, technical advisory, and training to ensure that companies meet quality, safety, and sustainability requirements. With that, let me pass you on to our speakers who will bring you through our risk-based approach to TDD, as well as the risk that they have observed in the cases that they may have helped to mitigate.
Good morning, everyone. Thank you, Corinne, for the introduction. As you said, my name is Magdalena Feil, and I will give you an overview of our experience with geothermal plants, why clients come to TÜV-SÜD for these kind of topics, and how our due diligence approach looks like. Here you can see So TÜV-SÜD has experience in geothermal plants since about 2005, and here you can see an exemplary list of projects we have conducted. The type of clients ranges from German and international investors over producers of components and EPC contractors to smaller and bigger communities who want to build a geothermal plant in their community. The type of project ranges from technical due diligence for a geothermal plant as a whole to the evaluation whether certain components are suitable for a specific project. So why do our clients actually come to us? There are, of course, many different issues investors or communities face, but I want to talk about two main pains, which I explain on this and the next slide. So the first pain is that clients are often afraid that they are not identifying all potential risks prior to their investment decision. So what are these risks with regard to geothermal plants? We have listed here a couple of examples, and I just want to go through some of them. So one risk clients face, one risk which needs to be identified beforehand is the exploration and production well risks. That means, or especially the exploration risk refers to a potential dry well, or that the reservoir provides not the expected temperature or production rate. Another risk is drilling risks. That's more related to the mechanical part of exploiting a reservoir. So, for example, there can be technical issues related to drilling. Other examples is negative public attitude by the people living nearby, supplier availability, as only a limited number of suppliers is available in this area. There can also be corrosion effects conflicting plant availability. Of course, tectonic dynamics is a big issue with regards to geothermal plants. Hazardous residuals, which need special disposal, and of course, with any plant reliability of production plants. The second issue clients face is that even if they have identified all risks, they wonder whether the CAPEX and OPEX required to mitigate these risks is covered in the financial projections, and if not, how much it would be to mitigate a specific risk identified. Examples here is that there could be an increased OPEX demand if injection pumping is additionally required for the reinjection of thermal water, which has not been expected beforehand. There can also be unexpected cost and time overrun in construction, as there is, for example, a dry well. Here's always the question, is this covered in the financial projection? What is there? Is it sufficient? And if not, how much can it be? So how does TÜV help to overcome these two pains I have just explained? TÜV helps with conducting a risk-based approach throughout the entire project life cycle, which means that we offer feasibility study in the concept phase. We can offer technical due diligence both in the design and in the operation phase. And last but not least, construction monitoring during construction. So we cover both greenfield and brownfield projects, and we can adapt our approach to different needs of different stakeholders, ranging from investors and banks to the actual planners and EPC contractors. Thereby, the main advantage of having a risk-based approach is to have a comprehensive approach and a transparent risk portfolio. And this risk-based approach, I want to explain a bit more detail on the next slide. So how does the risk-based approach look like in detail? TÜV applies a so-called risk matrix, and this you can see exemplary on the right side. That means that we evaluate each identified issue based on its frequency of recurrence and the expected operational and economic consequence. And to have more tangible results, which is understandable for each and everyone, especially for non-experts with geothermal plants, we translate these evaluations into risk acceptance classes, ranging from 1 being the most acceptable risk to 5 being not acceptable. So here on the right side, you can see the one on the very left side, so the most acceptable in green, to the not acceptable 5 on the very right side, which is colored in red. So our goal is, to have a comprehensible and transparent evaluation. But what do we actually look at? So which issues do we analyze with the risk-based approach? Although the word technical due diligence might imply that we only look at technical aspects, that is not the case. We do much more. So not only the topic assets is covered, but also other topics such as management, health, safety and environment, and regulatory requirements. So some examples in this respect is, for example, that the team so we analyze whether the team has sufficient expertise in this area, and if, for example, all knowledge and expertise is only with one person. So that is often the case for smaller companies, and that's, of course, a risk. We analyze, for example, whether all environmental permits are considered and whether they were received from the specific governmental institution. Also, we check whether construction permits are available and whether they were received from the specific governmental institution. If risks were identified, we then look at the business plan and we evaluate whether all related costs are already covered to mitigate the risk sufficiently. And if not yet covered, we give estimations what we think would be appropriate. So some further examples we can look at if required. So it always slightly depends on the specific project and also of the client what is needed. So some other examples is, for example, natural hazards, cybersecurity, also insurance issues, but it really depends on the specific project. So how does a technical due diligence process exactly look like? Also here, it always depends on the exact project and also what is required from the client, but often a buy-side due diligence looks as follows. We start with a so-called pre-analysis and red flag evaluation, where we highlight the so-called showstopper. So that's often based only on a limited amount of information, so-called information memorandum. We also look online what is publicly available, and of course we go through documents which is provided by the client and the seller. After a more detailed analysis, which includes Q&A with the seller side and, if possible, interviews with the seller or even the management team, we finalize our evaluations in the final due diligence report. We also, in this phase, we try to do site inspections. It depends on the project, but we think that that's very important during the evaluation, so we try to do this as often as possible. But the final report is most of the time not the last step. Often we are requested to support also in the closing phase of the investment. This can be in form of reliance and release letters, or we support in the purchase agreements from a technical perspective. So, for example, warranties and guarantees. So this is the last slide from my side, and I just want to give an overview that we are active in a couple of areas, not only in geothermal plants. And the advantage here is that many of the topics overlap and interrelate. So of course, what we learn in one sector, we can bring in our projects of geothermal plants. So now I give over to my colleague, Alex. All right.
No, it's Rolf this time. So what I would like now to introduce, ladies and gentlemen, are the risks in the early project phase. And usually we divide a geothermal project into two parts from the project scope. It's the subterranean aspects of the reservoir we are looking at, and on the other hand, the above ground installations, which usually relate to the power plant. And now we go into detail and have a look what are our experience and what are best practice if we have a look on the most risky aspects of a geothermal project, and there we are looking at the exploration risk. What Alex and me are doing now is to give you examples which should give you indication where typical and risky issues if you have a planning of a geothermal power plant or you do operate them and want to optimize them. The examples are taken from Germany. They are usually the power plants situated in the Rhineland-Palatine area, which is the Rhine Valley. And there we have a couple of geothermal power plants in the range of 5 megawatt electric power output. In the first project, it's a 4.7 megawatt electric geothermal power plant. We did a feasibility and technical diligence services to give a backup for the decision of an international investor to put capital into this project. The issues the investor was, of course, aware of are the exploration risk. Exploration risk relates to the risk of not having successfully found the minimum level of thermal waters which are needed for the production and the later operation of the power plant, which means the minimum flow rates of the thermal water are not achieved, or the reservoir temperatures are not that high as planned or expected. To make an analogy, it would be the same as if you buy a car and the engine is not as you expected, has not 200 horsepower but only 20 horsepower. That would be the risk and the problem. Okay, it would move, but it would not move in the way you have expected it, and it would bring you with 200 kilometers an hour to a place, but only with 50 kilometers an hour. The exploration itself determines target coordinates where the later drilling passes for the production well will be placed. And there we are not only talking about the depth of the drilling, but also of the horizontal, the longitudinal deviations of the drilling, which means we do not go vertical down, but we also can move aside to have extensional or translational active fault systems reached where usually the thermal water is located. But, and now the big but comes, everything we are doing here is underground, so there is a lot of uncertainty which typically accumulate over these early phases. And the risks are we do not find any reservoir down there, which is a so-called dry well, or, as I mentioned in the beginning, not sufficient production of thermal water, or lower thermal energy of the water, or we have very fancy water chemistry which will cause corrosion to our components, and we need to redesign our pumping system and the power plant system, especially the heat exchangers. What can you do to control this risk in the early phases? The first thing, of course, is to have a in-depth understanding of the very geological structures you're drilling at and you're aiming at to place your geothermal plant, the history of the geological structures, and, of course, the predominant systems of tension of the tectonic and seismic. To do so, you apply two-dimensional seismic analysis, but also three-dimensional seismic analysis for the location of the fault zones and the target zones, which enter and give you the data for the later modeling to have an exact definition of the places where to do the drilling. But these are not only static models, as you might presume. You have a lot of presumptions, and as geological structures are really alive, you also have to simulate the dynamic characteristics of the site, how they will change in future, which could lead to problems. For example, if you have already placed the drilling and the reservoir is operating for, let's say, 5 years very well, but then due to the seismic activity, the drilling hole will be blocked by the seismic characteristics or by new faults which are opening there. What you can do against it, the easiest way is to do it with a monetary mitigation, which means you have appropriate insurance coverage for dry hole and the drilling risks. And on the other hand, of course, another recommendation is to have, of course, high-quality geological drilling plan and experienced drilling companies who do, on the one hand, the exploration, and on the other hand, of course, the later drilling. And most of these companies are operating in the origins in the petrochemical industry to look for gas or naphtha reservoirs. If you look in detail, I present you an example of a so-called two-dimensional seismic data sheet. On the left hand, you see the raw data, which shows in the end the layer of the rocks going down to the basement where we have the old sediment of granite. And if you follow it from the top of your screen to the bottom of your screen, you then interpret these layers and you see the typical rock formations in the Rhine Valley, starting with the upper Pleistocene sands, going down to the tertiary base and cuprate layer, down to the limestone and redstone layers, where usually the reservoirs are located. Now you only have one cut down into the earth. What we do now is, based on a lot of assumptions, which are the expertise the geological experts bring into these models, a three-dimensional model is developed, which shows very precisely where the interested layers of rock are located. And usually, as I mentioned before, this is the shell limestone and the red sandstone. And based on these models, you can also introduce then the dynamics on the one hand, and on the other hand, you can very precisely locate where typical indications for thermal water reservoirs are located. And this is something we now look in detail. To make it more transparent, I took a two-dimensional slide and picture, and there you see on the lower third of the diagram some blue areas, and exactly in these areas the reservoirs are expected. And the indication are the rock formations, are of course other parameters we know from the three-dimensional seismic analysis, and nevertheless it can happen that there is nothing down there where we do the drilling. And so we are talking about a so-called POS if we do this project, which means the probability of success. And in our project, the depth of the limestone has been derived from the three-dimensional seismic model where the reservoir is expected, and this was down to 2,330 meters. And this led to the calibration with additional borehole data we had already conducted. The problem was that for this depth, hardly any temperature values exist. The amount of data for this area had been quite low, and the rating was not that reliable. So we did some testing, drilling, and based on the temperature gradients we received from 27 boreholes around this area, we had a calculation of a likelihood of success of 82% for a temperature of 129 centigrades in 2,330 meters. In the end, effectively we came to 127 centigrades, but we could cope with this small delta quite well with the later power plant. Another risk in the early phase is, of course, the risk of cost overruns. Because of the quite high uncertainty in the drilling exploration phase, we have, of course, an idea from comparable projects what the capex will be. But due to the rock formations or not expected fault configurations, or even problems with the drilling as a stuck drilling head, it could occur that the time will take longer to find the reservoir, or on the other hand, it could also be a more complicated drilling, which could result from different issues going there. And the project we had there is also located in the Upper Rhine Rift Valley, and it was a 408 megawatt electrical ORC power generation plant. It was, on the one hand, the feasibility and technical due diligence we investigated there for an international investor. It was a investment form. And of course, we also, and this is what later Alex will tell you, did on the later running project optimization in the operation. For risk of cost overruns, of course, the determination of the expenditure risk regarding investment volumes in the drilling and the later power plant construction phase are essential inputs data for the financial model and, of course, on the later return on invest and of the project. Our experience with comparable geothermal projects in Germany, but also in other locations as in the US and in other European countries as in Italy, in Turkey, and also in France, we have, of course, benchmarks developed which allow us, of course, in consideration of the specific geological situation of the power plants, to have a quite comparable database for new greenfield geothermal projects, and if these projections are within what we would expect and what is good industry practice. And from that we learned, of course, that the budget for investment in the subsurface structures, which is the drilling and the pumping, is an average 70% of the total invest of a geothermal project. And in the project I took as an example, we had calculated drilling cost of 25 million euro, and the power plant budget was approximately 9 million euro. And given the relation of the total costs, this ratio conforms to our benchmarks for geothermal power plants quite well. Taking the real-term benchmarks from 2009, honestly, we have to, of course, usually correct them according to the price development. We have a lower limit for the capex for drilling of 4.4 million euro for per megawatt electric, and an upper limit of 5.8 million euro per megawatt electric, and the median of this 90% confidence interval is about 5 million euro per megawatt electric in 2009. The benchmarks we have there usually include 2 wells we had looked at, so 2 drillings, and includes also the site development, insurance, and financing of all these things. Besides these 2 exemplary issues, and which are, from our experience, the big risk driver in the early phases and in the subterranean activities for constructing and planning a geothermal plant, there are other typical issues we evaluate. And of course, this is how this technical and uncertainties are reflected in the financial model of the business plan. We derive sensitivity analysis from a technical point of view of all relevant parameters which could lead to a project failure. We, as I explained already, do benchmarks with comparable projects. We determine critical project steps in the planning, including the supply chain, but also the drilling and the power plant construction. And we have also a look on the entire planning and management of the construction and commissioning of the plants, and then do on the site acceptance testing, also accompany the performance data if they are according to the contractual expected values. We have a look on the insurance model and also check whether the power purchase agreement, if we have electrical outputs, are according to what the performance data are expected to deliver from the power plant. And at least, of course, authority also have some words to say. We have a look in the early phases on the permit situation, whether there is, of course, the permit for the drilling. We support to get these drilling permits, and, of course, on the later construction building permits for the above ground constructions. So I would now like to terminate my long talk. I hope I gave you an idea of the early risk drivers of geothermal power plants, and I hand over to my colleague Alex, with whom I usually perform as a core team and as the face to the customer geothermal power plants. So thank you very much for your attention. I'm looking forward to your questions.
So, hello. As Rolf mentioned, the underground part of the power plant project, we have also to cope in a scope of feasibility and technical due diligence with the overground part of the plant, so the plant section itself. And there could also be some crucial things we have to cope with. We have some risks, we have some faults, and so this part will be about this one. As first slide, we have to cope with the risk of leakages. There's a lot of pipings and technical installations above the ground, and there is always a risk of leakages. I'm talking about the same project as Ralph before in the Upper Rhine Valley in Germany with the overseas power generation of 4.8 megawatt electrical. And this was a feasibility and technical due diligence, of course, for the investment. And they wanted to evaluate the current situation on site and also a possible production extension scenarios to increase the power output and, of course, the value of the power plant. As we detected on site in a visible inspection of the power plant and within the documentation the investor and the operator gave us, we detected a leakage problem in the isopentane cycle, which occurred a couple of months before our visit. The evaluation resulted in a faulty code in the software system, which operated the pump, the isopentane pump, against a closed valve. And this produced a higher pressure inside the piping system and produced leakages at the valve and also at the piping, which brought a lot of damage to the operator, which had on the one hand to cope with the environmental problems of emissioning the isopentane in the environment and to cope with the safety issues for his employees. And of course, this causes also a financial disadvantage for the operator with the shutdown of the power plant and all the repair costs we have to cope with. Our evaluation shows that a sensoric and detection state of the art was installed, and this localized the leakage and the hole in the valve in a very fast way. As a second part, the immediate shutdown of the process, which was triggered by an automatic control system, minimized, of course, the risk of emissioning the isopentane in the environment and threats the operational staff on site. And so they had the chance that the power plant was shut down immediately. The third part we detected was that the fast repair and the restart process was realizable due to a competent, experienced service team on site and, of course, a sufficient spare part supply they had on site. So they had to repair it fast and they could go online in a quick way. The last thing that should be done was the redesign of the software tools. So they had to do a deep review and analyze of the software and redesign it on where it was necessary. Besides the leakages in the piping, we have also concerning the pipings and power plants parts, which comes from the chemical composition of the thermal waters, which is the clogging and scaling in the piping. To mention the project in the Malm area in Bavaria, near Munich. This project was a comparison and evaluation of the technical solutions for the power plant, and the investor and the operator wanted to know which technical solution would be best for the operational phase. Due to the, as mentioned, due to the chemical composition of the thermal water, which is quite critical in the Bavarian Malm area, we had to cope with a lot of clogging and scaling within the piping, in the pumping, and also in the plant installation itself. So this has a major problem, for example, with conventional heat exchangers. So the heat exchangers loses all their calculated power, and as a result of that, we had a lot of leakages and damages throughout the corrosive water, and reduces, of course, the performance of the leak exchangers and throughout the scaling effects. The result of our evaluation was to increase the cleaning processes. The number of cleaning processes had to be increased. We had to implement a strict regular inspection protocol. It's a kind of management they have to implement. And as you can imagine, not the cheapest solution would be, we advised to install a new kind of heat exchanger, which was in this case made of titanium. As I know, it's working still in a good condition, and they have no problems with them anymore. What brings us to the next risk that could occur during the operation of a power plant would be the risk of a low power output itself. Brings us back to the Rhine-Rift Valley, again in Germany, with the ORC power plant we mentioned before, and Rolf was talking about. With respect to the performance of the cooling system, recooling system, mostly on the top of the power plant, on the rooftop, we had to face their efficiency loss during summer times, which means that during the warm summer times we have a smaller delta T compared with the ambient temperature in the cooling section, while in January, February, and March, as well as, of course, in November and December, the winter, the gross efficiency is an average, as we detected, higher than 40%. In the warmer summer months, instead, the gross efficiency decreases to an average of about 11%. In this case, and we had the annual average results in an average of about 12.5%, which is lower than expected and lower than calculated in the financial business plan, and in the financial. This brought a lot of disadvantages for the power output, of course, in a financial way. Our solution for that, we advised the operator and investor to improve the whole feasibility through installation of additional cooling units on the roof. They had enough place for it, and in order to increase the gross efficiency in summer times. So we had to cope this delta T with an additional installation. As a substitute to the precise design and the OPEX trade-off, of course, a pragmatic solution could be to extend the existing air cooling installation by an additional cooler bore and integrate this additional cooling capacity in the temperature-driven control loop of the cooling system. which means that we have a higher cooling power which compensates the delta T, the degraded delta T for the summertime season. As a result of the scaling problem, as a result of the composition of the geothermal water, we have also detected a risk for the environment and for the personnel on-site and in the surrounding of a geothermal power plant. Also occurred in a project in the Upper Rhine Rift Valley in Germany. We detected that on-site were stored several containers and barrels with waste resulting from the construction period, also from cleaning of the filters, from cleaning of the pipers, cleaning of heat exchangers, and all the remainings, all the scalings and foils and materials they have to work with. They were stored on site in a garage, and this waste was low radioactive waste. They have to treat it separately and exclusively. This waste is slightly radioactive and has to be treated in a specific way, of course. Risks for the environment are possible, also the risk for health of the humans, and as a result of that, the financial aspect are given. This is, of course, also as a result of that could also be an impact on the reputation of the project if you have to store radioactive waste on a green geothermal power plant area. As a solution for that, we advised the operator to implement a management system, a functional waste management system, with one responsible person for it, who copes all the storage, who copes the waste management. As a second part, regular measurements and tracking of the radioactive exposure is important. Always to know how much radioactive exposure we have on site. Is it dangerous for the staff and for the people around, and how to cope with that. And if possible, to realize the disposal via a securely contracted disposal route, of course. In this case, it was a bit difficult because the radioactive waste was of that low amount of waste that the official disposal route for radioactive waste was not possible to go. So as a solution, we advised them to try to find other power plant operators to increase the amount of waste and give it to the contracted disposal. As that you can see, so there's one risk following the other, and there are different kind of risks you never would think of, but you have to cope with during construction, during operation, during disposal, and during the whole life cycle of the power plant. And within the technical due diligence and the feasibility study, we cope with all of that kind of risks and try to find some solutions for the operator and investment companies. This brings us to the end of this webinar. As a summary, we have two questions that could be answered. The question one is if the risk portfolio is not comprehensive enough, what could be done? So we had to adopt a risk-based approach to have a comprehensible and transparent risk portfolio. It's major important in the concept, in the exploration, and of course in the basic detailed design, in the construction, and in the operational phase. So all over the whole life cycle. And the risk areas that could be covered within these TDDs and these investigations would be the whole assets, the management itself of the whole plant, the regulatory requirements on noise emissions, environmental, for example, construction requirements. We have to cope with all the standards and norms that are important on site in this country. And of course, we have to cope with the health, safety, and environment HSE topics. And you can see, so we cover all the risk areas that are imaginable to cover. The second question would be if it's unclear whether the measures to mitigate the identified risks are covered in our financial plan, in the financial business plan. And these questions could be answered with that we have to look at the business plan in advance and evaluate whether all the costs are related, are they mitigated, are all the risks identified and already covered within the business plan, and if they are not covered yet, that the account of the additional CapEx and OpEx is based on how much each mitigation measure could be. So the value for investor and operator could be a close cost-related perspective that can show is the CapEx, OpEx, and are all the risks within the CapEx, OpEx mitigated. So this is from my part the presentation for the webinar, and yeah, thanks, and hope you have some questions we have to answer.